All right, welcome to Lecture 13, Chapter 3, Section 3, where we'll be talking about molarity. Okay, molarity is a measure of concentration. That is to say, we're talking about solutions. So a more concentrated solution has more stuff in it. Okay. So molarity specifically, you have 1 molar is equal to 1 mole of solute per liter of solution. So remember, solute, thing dissolved. Solution is solute and solvent, where the solvent is the thing doing the dissolving. Okay, so solution, whole thing, solute is, the thing you're focusing on. Okay. So let's look at how to prepare 1 liter of 1 molar sodium chloride in water. Okay, so this is a saline solution, a saltwater solution. First, we need to figure out how much sodium chloride we're talking about. Then we can go about dissolving that in water. So, 1 molar means 1 mole of NaCl in the 1 liter of solution. So we have 1 liter of solution. So 1 molar is 1 mole per liter. That's where this came from. That's just the definition of molarity, 1 mole per liter. So if we have 1 liter of solution, then liters of solution cancels out, leaving us with just moles of sodium chloride. So it's going to be 1 mole of sodium chloride. Now, although moles are very convenient, you can't measure those out in the lab. You need the molar mass, grams per mole, of sodium chloride, before you can figure out how we're going to make this solution. So, let's pop over to the periodic table. All right, and we look at our numbers. Okay, and we look at our numbers, and here is sodium, the molar mass of 22.990. Over here we have chlorine. Stop fidgeting. Chlorine at 35.45. So we add those together, and that gives us a molar mass of 58.44 grams per mole. Hope you don't mind that I did the adding already. So 1.00 moles of NaCl times 58.44 grams of NaCl per mole of NaCl. Moles cancels, leaving us with 58.4 grams of NaCl. Wait, 58.4? What happened to the other 4? Well, sig figs. I am trying to keep track. Okay, so 58.4 grams of sodium chloride is what we weigh out on the balance. Huzzah. How do we get from there to, anywhere else? Well, what we need, what's usually used, I should say, is a volumetric flask. Flask that looks something like this. Okay. There might be, things written on the side, like 1.000 liters or something, however well it's calibrated, how well it's made. It'll probably also say something like TC. But it's just a flask that is good at measuring to a very, very, very well. It measures very well to a single volume. Okay, hence volumetric. Whereas a graduated cylinder can measure a lot of different volumes, it doesn't measure them nearly as well. And they are usually marked TD. TC and TD means to contain. TC is to contain. TD means to deliver. Okay. So when you pour up to the calibration mark on your volumetric flask, this line partway up the neck, that gives you very precisely the amount of volume inside the amount of liquid contained inside the flask. But when you pour it out, you're going to have a different volume. Whereas these guys are marked TD, graduated cylinders are marked TD, that means to deliver. So when you measure out whatever volume's in there, you measure out to the line, 58 mils or 47 or 50 exactly, whatever. It doesn't have that much inside the graduated cylinder. It's after you pour it out. That's how much it should deliver. Okay. So it's just, we try to be careful about these things because being careful saves time, money, and occasionally lives. All right, so you work with a volumetric flask to make your solution because you want to get the volume as right as possible, as good as possible. So what you do is you dump your solid in the bottom, your 58.4 grams, and then you fill it up partway with water, and then you swirl it around until the salt, in this case, is all dissolved. And then you fill it up to the line. Remember, you always want, when you're looking at it, you want the meniscus to be at the line when you're looking at it at eye level. Okay. You always want the meniscus to make the line. It's just that sometimes you'll have a downward-facing meniscus, sometimes you'll have an upward-facing meniscus. That just depends upon what liquid you're talking about and how it interacts with the walls of the container. Water is usually a downward meniscus, like this one over here on the left. All right, so you mix it up, you swirl it up, you fill it up part way, dissolve all the salt, then you fill it up the rest of the way. And you swirl it around enough to get it all mixed up together. Why do we do it this way? Well, because of what's written on the bottom of the definition of molarity. 1 molar equals 1 mole of solute over 1 liter of solution. That solution is important. The word solution, I should say. When you add a solid to a liquid, the solid dissolves, but it doesn't disappear. It's still there. It's going to add something to the volume of the solution that you dissolve it in. So if you were to fill up to the line and then add your solid, you would have a different volume. It wouldn't actually be, 1 molar or whatever. Okay? You would get the wrong concentration. It wouldn't be a huge difference, but it would be a significant difference, especially when you deal with very, very small concentrations, as occasionally happens. So put in your solid, then fill to the line. That's kind of a big deal. And be careful about filling to the line. If you go past the line, well, you're kind of screwed. And there's no easy way to measure the difference in volume there. So here you put in your 58.4 grams of NaCl. You add, a couple hundred mils of water, swirl it around, and fill it up to the 1 liter mark. And that's how you get your 1 molar solution of sodium chloride. Now, what if it's not a liter? I mean, a liter is kind of a lot. Okay, what if you only want a quarter liter? Say 250 mils. Okay, a mil is equal to, that means, a milliliter. That is to say 1/1000th of a liter. Okay, so 250 mils means a quarter liter. We know this because 250 mils times 1 liter per 1,000 milliliters is equal to 0.2500 liters. Now remember, this is a precise conversion, so infinite sig figs. So our answer is based on this. 4 sig figs, 4 sig figs. All right, so we're looking at 0.2500 liters. And 0.2500 liters of solution times 1.00 moles solute. Well, it's moles of sodium chloride per liter of solution. So liters cancels, leaving us with 0.250 moles of NaCl. And 0.250 moles of NaCl times 58.44 grams of NaCl per mole of NaCl. Moles NaCl cancels, leaving us with 14.6 grams of sodium chloride. So once again, you'd break out the volumetric flask, but this would be a smaller volumetric flask, only 250 milliliters, and you'd only be adding, and you'd be adding 14.6 grams of sodium chloride, and the result would still be a 1 molar solution. So that's some examples of doing math with molarity. Let's do some in a different vein, a different direction. So first, here's your equation. For those who like to memorize equations or look at them, M equals N over V, okay? Where V is the volume of solution, N is moles of solute, whatever's being dissolved, and of course capital M is molarity, with units of capital M, which means molar. And this is moles, and this is liters. Liters of solution, moles of solute. Okay. Oops, I got those backwards. All right. So that's one way you can have it. And rearranging to solve for the other two, you get N equals mv, and V equals N over M. But I would not recommend memorizing those. Just remember the units of molarity. It's moles per liter. Moles per liter. And then you can rearrange, so long as you can do algebra. So, here's a problem. What is the concentration? This is one way we write concentration. We'll put brackets around whatever we're talking about. So in this case, it's the concentration of glucose. If you have 12.50 grams of glucose in 375 mils of solution. So glucose, if you don't remember, is C6H12O6. So you're going to need to find N, the moles, is equal to 12.50 grams times moles per gram. So we're dividing by the molar mass of glucose. Glucose has a molar mass of 180.16. You can double check me on that one. So when you do this math, the number of moles is 0.06938 moles glucose. We also need the volume of our solution here. We have that, but it needs to be in the correct units. You're going to need to go ahead and convert this from milliliters to liters. That's a nice simple conversion. You divide by 1,000. You move the decimal place 3 to the left. Remember, bigger unit, smaller number. So our volume, volume is equal to 0.375 liters of solution. So now our molarity, our concentration, is N over V, or 0.06938 moles of glucose divided by 0.375 liters of solution. And that is 0.185 molar glucose. That is the concentration of glucose in that solution. All right, let's flip it around a bit. Let's solve for something else. Okay, so what mass of potassium phosphate makes 125 mils of 0.750 molar solution? Well, potassium phosphate, it's an ionic compound. Potassium is just K. Phosphate is PO4 3-, so we need 3 potassiums. Potassium is potassium 1+. Phosphate is PO4 3- across the streams. K3PO4. All right. So the molar mass. Thank you. Molar mass of potassium phosphate is 212.264 grams per mole. The concentration is 0.7550 molar. The volume of our solution in liters, we bring it 3 to the left, 0.1250 liters. So we have M equals N over V. So N equals MV. Plug in our two numbers, 0.750 molar times 0.1250 liters. Remember, this is moles per liter. Liters will cancel out, leaving us with moles. And what that gives us is 0.0938 moles of potassium phosphate. I'll need to clear off some room because I didn't ask for moles, I asked for mass. That's why we're going to need this here. 212, 264. So 0.0938 moles of potassium phosphate times 212.264 grams potassium phosphate per mole of potassium phosphate. Grams per mole is the molar mass. So moles cancels, leaving us with grams. And what that gives us is 19.9 grams of potassium phosphate. That's what you're going to dissolve in the 125 mils to get your 0.75 molar solution. And that's your answer. Let's mix it up some more. Let's look for volume, why don't we? If you have 21.725 grams of ammonium chloride, and you want to make a 1.30 molar solution, what volume solution are you going to have? Well, we're going to need to convert this to moles, and then we'll also need to solve this solution for V. So, to convert grams to moles, you need the molar mass. So we also need to know what ammonium chloride is. Ammonium chloride is an ionic compound involving the polyatomic ion ammonium and the monatomic ion chloride. You cross the streams and you get NH4Cl, 1-to-1. And 21.72, that's an ugly 2, 725 grams of ammonium chloride times moles per gram. What's the molar mass of NH4Cl? It's 53.49 grams of NH4Cl per mole of NH4Cl. That is equal to 0.4062 moles of NH4Cl. Now we have N, we have M. When we rearrange this, we get N equals mV by multiplying both sides by V. Now we divide both sides by M, we get V equals N over M. So V equals 0.4062 moles of NH4Cl divided by 1.30. Now remember, molarity is moles per liter. That's moles of solute per liters of solution. So that's 1.30 moles of NH4Cl per liter of solution. So moles are going to cancel. And in terms of units, you'll have 1 divided by 1 over liters. So this is going to come up top. You're going to be left with units of liters of solution, which is good because that's exactly what we looked for. And the number, 0.312 liters of solution, or 312 milliliters. All right, so those are some examples of the different things you can solve for regarding molarity. Okay, I mean, you have 3 things in your equation, M, N, and V. So those are the 3 things you can solve for. You can make it slightly more complicated by talking about the mass of your solute instead of the moles of your solute. You might have to convert to milliliters of solute, of solution, but that doesn't change too much. That's just a conversion factor tacked on to the beginning or end of your problem. And conversions, hopefully, are not a problem for you. Not a serious problem, anyway. Not anymore. So let's go ahead and talk about dilutions. Now, a dilution is when you take a small quantity of concentrated, so this is concentrated, and you add water to get a bigger quantity that is more dilute. Okay. So this is your dilute solution. Okay, all you've done is add water. So when you do your dilution, what changes and what stays the same? Obviously, what changes is your volume. You've added water. You've gone from small to big. So looking at M equals N over V, this has changed. Okay, change. Another thing that's changed, just judging by the language I've used, you've gone from concentrated to dilute, so your concentration is also changing. What stays the same is N. Okay, the number of moles of solute hasn't changed. I was very deliberate about drawing my dots. You see, we have 8 dots here, we have 8 dots here. Okay, all you've done is add water. You haven't added any more solute. Okay, so the moles of solute are going to stay the same. So when you rearrange this formula, N equals mV, this is going to be true, and it's going to be the same before and after your dilution. So the concentrated mV is equal to the diluted mV. So one way of writing that would be M initial times V initial is equal to M final times V final. Okay, this is N initial in final. But these are the same. The number of moles hasn't changed, so these two are equal as well. Something that flows off the tongue a little bit more easily would be M1V1 equals M2V2. M1V1, M2V2. That is the dilution equation, and you're going to use it all the time. So, if you have 100 milliliters of a 0.850 molar solution of HCl, how much water do you add to get 0.500 molar HCl? Okay, so we're doing a dilution from high concentration to lower concentration. So how much water do we add? Well, M1V1 equals M2V2. Which ones do we have? Well, this is what we're starting with. We have 100 mils of 0.85 molar. We want to get 0.5 molar, so this is what we're looking for. So let's rearrange really quick and solve for V2. That means dividing both sides by M2. V2 equals M1V1 over M2. Now, here's a neat thing. When you're talking about dilutions, you don't need to change your volume. You're going to get the correct answer. It'll be in milliliters. No conversions necessary for dilutions is what I'm saying. So, 0.850 molar times 100.0 milliliters is equal to, or divided by, 0.500 molar. Notice molarity cancels, leaving you with milliliters. And when you do that math, what you get is 170 milliliters. For those of you who are hoping to catch me in a mistake, note the dot. We have 3 sig figs, because 4, 3, and 3. So you're going to have a final volume, of 170 milliliters. But if you rewind the tape, you'll find that's not what I asked for. I asked, how much water do you add? And that means 170 mils minus 100 mils. And your answer is 70 mils of water. So you start with 100 mils of hydrochloric acid, and you add 70 mils of water, and that's how you'll get your final concentration of 0.5 molar. Although, technically, do what you ought to, add acid to water. You should be adding the acid to the water. Add 100 mils of acid to 70 mils of water in order to make this dilution safely. Okay, if you add 30 mils of water to 125 mils of a 0.375 molar solution of nicotine, what's the final concentration of nicotine? Well, M1V1 equals M2V2. Our initial concentration, we have that. It's up here. That's 0.375. Our initial volume, that's this guy right here. That's 125. We're looking for the final concentration. We have the final volume. It's not 30. Instead, it's 125 plus 30, because we're adding 30 mils of water. So, our final volume is 155.0 mils. So we, solve for M2 equal to M1V1 over V2. That is 0.375 molar times 125.0 mils divided by 155.0 mils. Milliliters cancels out, leaving you with molar, and an answer of 0.302 molar nicotine. Now, does this answer make sense? Well, in short, yes. Because bigger volume, lower concentration. You've diluted your solution. So it's gone down from 375 to 302. Why would you dilute a solution of nicotine? I don't know. Why would you have a solution of nicotine in the first place? Starting from a 3 molar solution of sodium hydroxide, how do you make 500 mils of 0.250 molar sodium hydroxide? This one's a little bit more straightforward. M1 V1 equals M2 V2. Well, we have V2, that's the 500 mils. We have M2, that's our 0.25 molar. We do not have V1, that's what I'm asking for. What volume of 3 molar sodium hydroxide do you need to dilute to get to 500 mils of 0.25 molar? And the initial concentration is 3 molar. So we rearrange, we solve for V1. V1 is equal to M2 V2 over M1. And that is 0.250 molar times 500 mils divided by 3.00 molar. Molars cancel, leaving you with mils, and your answer is 41.7 milliliters. So that's the volume you start with. How much water do you add to get there? That's that. Now, how much water do you add? Well, that would be 500.0 minus 41.7. You add 458.3 mils of water. Or, technically, I suppose, you add 41.7 mils of sodium hydroxide to 458.3 mils of water. Do what you ought to add acid to water. It also applies to bases. It just doesn't scan as well. Do what you ought to add base to water. Do what you ought to add base to water. You know, it just doesn't have the right beat, not the right rhythm. Now, suppose you need to make 100 mils of 0.250 molar sulfuric acid. What should you use? A 0.1 molar solution, a 0.5 molar solution, or a 1 molar solution? These are all H2SO4. Well, either one of these two would work. Okay, you'd either start with 50 mils of this guy or 25 mils of this one. This one, not so much. Why? Well, you can do the math and you'll see that the numbers come out kind of weird. Okay, M1 V1, M2 V2. You have V2, M2, and M1. You're looking for V1. V1 is equal to 0.250 molar, where you're going to goes on top, times 100 mils divided by the initial concentration of 0.1 molar. Molars cancel, leaving you with 250 milliliters of the original concentration, 0.100 molar H2SO4. What would that mean? In a way, it's not ridiculously impossible. You could just basically evaporate this down or boil it off, to go down from 250 mils to 100 mils. But I really wouldn't recommend putting, concentrated sulfuric acid on a hot plate and trying to boil off some of the water. That's what they call a bad idea. Don't do it. But, you could. Just don't, ever. No. Boiling acid is not a fun thing. But either of these two, the more concentrated ones work. You want to make a dilution, start with the more concentrated thing. All right. And that does it for concentrations. I will see you... Well, it doesn't do it for concentration. It does it for molarity. Yeah, I'll see you next time when we'll finish talking about concentrations.